Well, I hope you guys are happy, okay? I hope you're happy because it finally happened, okay? You broke my arm. All those years of gaming have caught up to me, and now my wrist is broken. Just kidding, my wrist is not broken, although it is injured. Although it's a lot better, but I'm still wearing this brace on it just to keep it safe so that I can't break it anymore. But yeah, so that's that. Yeah, I was trying to find out how to multi-stream. Apparently, so I was going to use Streamlabs, but turns out Streamlabs multi-stream is only available for Ultra, which is like, how much is it? How much is the price of this? $19 a month? Are you kidding me? Or $150 a year? Are you kidding me, bro? Are you kidding me? No, I'm not doing this. Stream from Xbox. Is it just Xbox? You can stream on PS5 for free, all right? But because I was thinking, oh, I should do multi-stream. I should stream on, YouTube, Twitch, and Kick. Because why not? Maybe I'll get more stuff going on over there. But it's just not. I'm not gonna pay that much money to do it. And also, like the layout of it is horrible. Streamlabs layout just looks awful. I mean, like, hold on. Can I remove the mini feed, please? How do you remove the mini feed? I don't know if you can. But like the layout just looks weird, man. It's like trying to make it like all, like blah, blah, blah. Like it's all modern. But it just looks bad. The OBS layout is so much better. So much cleaner, so much simpler. And you know what's happening. Hello. Hello, me. Wait. Hey, you. Hey, you. Yeah, it's funny. That's some good content right there. Anyway, let's get the stream set up. Fuck. So what are we doing today? You might be wondering, what are we doing today? Well, it's very simple. Okay, what we're doing today is what we've been doing for a while. All right? We're studying some physics. What else? Study with me, physics, work, grind set, motivation. What other tags? What other tags can you guys come up with? Study with me, physics, motivation. What else? Also, I'm starting to question if I even need to use a pop filter when I'm like streaming. Like, does it really increase audio quality that much that it's worth like having this circle that's around me at all times? I don't actually know. I don't know if it's worth it, but it might be. Okay, work, grind set, motivation. What else? You can do it. Save. All right. I know nobody's going to watch this though. That's okay. I think I need to change my thumbnails. I think I need to make my live stream thumbnails better. Yet another thing to add to the list. So I am actually kind of torn whether or not I should read solid state physics or if I should read Math. I'm trying to see like which one should I fucking lock in for. But I think I should lock in for all. So we might as well just read solid state physics, see what happens, right? And then move on from there. So we'll do our similar thing. Also, update from midterms. I think ChatGPT for things like real analysis might not be the best option. Now that I think about it, it might not be the best option. But you know what? It is what it is. I think it led to some misunderstandings that caused me quite a few important points on the midterm. But you know what? What can you do? Am I right? What can you do? I'm also wondering if I should crop my image like on OBS like this. You know, something like this, and then just having it like that. Like, does that make it better? But then I'm like kind of off-centered most of the time, unless I'm like zoomed in here. So it's kind of a problem having it like this. I might just keep it like this. I don't know. I kind of like having the full width, full breadth of the display, you know. That's just kind of what I like, okay? Now I'm a little bit too off-centered. I don't know how to do it. Like, I don't know. I could do like the Forsen webcam where he's like, you guys know Forsen. Everybody knows Forsen. Where he's like down here. And then it's like this. I could do this webcam, but then this is just kind of weird. And you see my hand all the time. And you can't really see my face. And from the bottom, honestly, it's not too flattering of an angle, I gotta admit. So I don't know. Actually, let me... Sorry, I'm like checking the top of this to see if I need to... Kind of need to clean it. Not really, though. Yeah, or I can just do a dynamic camera. I'm not sure, but you know what? It is what it is. Wait. Okay, come on. Come on, dude. Okay, there we go. Cable management back. Hello. You're too low. Okay, now you're okay. Let's adjust you a little bit there. Okay. Anyways. Okay. I also need to get 10,000 steps in today. I didn't do that. And I need to go to the gym tomorrow. I need to go to the gym tomorrow. I need to go to the gym tomorrow. Okay. Wait. Let me just look at my calendar. Let me make sure I have all my homeworks noted. And I uploaded that homework for tomorrow. Yes. This would be homework 8, I'm pretty sure, right? Need to tighten the wrist brace a little bit. Okay, anyone else who uses a wrist brace and like, if I tighten it a little bit too much, I feel the blood restricting. But if I don't tighten it that much, like it doesn't keep my wrist in place. I think I bought too large of a size. I think I should have bought small. But my ass is like, oh, you know, like if I buy small, that means I'm a wimp. Like my wrists are bigger. But actually, it's like constricting my forearm first before my wrist. So I don't know. I tried loosening that part and then tightening the wrist more, but it still kind of feels like it's just restricting my blood flow. But you know, I guess it is what it is. You know, because like I don't want to use this and restrict blood flow because blood needs to flow in order to like, you know, heal it. Blood is the healer. Um, but yeah, wait. Let me just check. Let me check when this homework is due so I can note it in my calendar, okay? Please. Please. Just let me, please. Thank you. Please and thank you. Yeah, this is due April 10th, which is that date. Yes, yes, yes. Great. Excellent. Oh, yo. I should play some freaking Tekken right now. Oh, God. You know how tempting that is to play some Tekken right now? To grind some Tekken? It's so tempting right now. Is the compressor even worth it? Yes, the compressor is worth it. Yeah, compressor's worth it. I just wish it was a little bit stronger. Can I make the compressor a little bit stronger? Yes, I know. I'm going all over the place right now. Okay, whatever. I don't care. I don't care. I do not care, actually. Actually, I do not care. Okay, I don't care. Oh, yeah, I can change, like, the threshold and, like, the whatever and the whatever. Hello, 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 hello. I think this is okay. Attack needs to be more instantaneous. It needs to be an instantaneous attack. Okay. As soon as I talk, it needs to turn on. Release, gain can be fine. That gain is okay, I think. Can I not like monitor myself? Oh, it also does an EQ. I don't know if I want that EQ though. I'm not sure. Oh shit, I have the effect turned on. What's the effect? Oh, the effect is a reverb. Oh, so you've been hearing me with reverb that whole time. Ha ha ha. Reverb. I can do the reverb for a while. Like if I start talking like this. Anyways, Okay, anyways. That's the compressor dealt with. How does my voice sound now? Wait, it might sound totally off. It might sound weird. It might sound totally off. It might sound weird. It might sound totally myself. Oh, it also does an EQ. That's so funny. Speaking with the reverb. That's so okay. It's also good that what I hear and what you hear. The most important thing is that what I hear and what you hear is the exact same. Actually, no, the most important part is probably my audio balance as well. Audio jungle. But yeah. See those brain connections that I do? Anyways. I wish this monitor was higher quality because these words are kind of like, you know, tick tack tick tick tack tick. That's how these words kind of look. They kind of look tick tack tick. But yeah. I started putting lime and salt in my water. Try to be healthier. I don't know if it's working, but you know, it's worth a shot. It's worth the shot. Boo 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 boo. All right, guys. Yes. Okay, we've been live for 15 minutes and we've done nothing but just say a bunch of garbage. Okay, I get it. I get it. Ooh. No, no. That's a little weird. I don't want that harsh light. Instead, let's do something like that. Okay. That didn't do anything, but you know what? Whatever. Okay, it doesn't matter. Guys, I'm just procrastinating. Okay, let's read. They probably talked about powder diffraction today and then fucking, I don't know what else, dude. Let me actually check to see. Can I actually check and see? We are actually behind on what we should be doing. What would you say if I boom ba da 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 no? Last thing he uploaded was lecture 18. Okay, so he didn't actually upload the lecture slides or whatever. That's okay. We'll just read this. But, you know what we need? Of course we need this. Of course, dude. Of course. Come on, how could we go without good old 3DS music? Because there's someone who's upstairs, they're walking the 10-mile triathlon, okay? They're upstairs and they're just fucking walking. But we'll let them walk. I'll let them walk. But holy fuck. They're shaking the fucking roof. Like it's nobody's business. What's going on? I closed out my freaking live stream dashboard. I need that. So I can see that 0 people are watching me. That's pretty epic. Yeah, I think I need to change the thumbnail. I think the thumbnail is not bringing in people. I think the type of thumbnail I need is like a cozy, a cozy fucking background. There's no cozy background here, guys. There's just me grinding. Okay. I can also have like the webcam over there from the toaster oven. That'd be kind of cool. I'm getting kind of cold. Guys, there's like 50 million excuses I'm coming up with. Oh, but I do need the jacket. It was pretty cold today, okay? That's not just me making it up. It is cold. Oh, God. Okay. Let me get a jacket. I'll be right back. BRB. I need to change my whole... Ugh. I need to change my whole fashion shit that I got going on, man. My fashion's kind of fucked right now, but, you know, it doesn't really matter. You can have bad fashion, doesn't matter. Doesn't matter. Okay. In the last chapter, I need to just stop I need to stop, and I need to do. Okay, I need to stop, and I need to do. I'm so tired, though. So exhausted. Let's see. I can go to the gym tomorrow. Chipotle has a free delivery fee. Should I do delivery, guys? It's gonna be food for tomorrow, honestly, so... Like, I can order it and then just fucking put it in the fridge. Honest to God, man. This is for me. It's for me. Wait. They're trying to get me to pay fucking $20? Where's the place for me to fucking... Where do I... Can I do a promo code? Why the fuck is it still fucking $20? What the f... That makes no sense. I have to pay tax and a service fee and a tip on top of it. Never mind, guys. Oh, I can not tip them. That's kind of an asshole move, though. Why is it a minimum of... Oh. Tip a custom amount. $1? You know what? It's just not meant to be. It's not meant to be. It's not meant to be, guys. It's not meant to be. Never mind. I thought I could get, you know, something for pretty cheap, but nope. Never mind. Never mind, guys. Never mind. It's too much money. It's too much money, which is something that we don't have right now. Yeah, dude, we do not have money right now. Holy shit. That's okay. Now you gotta remind me to cancel my ChatGPT subscription in the summer, okay? Because the only thing I use this for is studying, and I won't be studying in the summer, I don't think. All right, in the last chapter, we discussed reciprocal space and explained how the energy dispersion of phonons and electrons... Now this music is distracting me. And now that... Dude, okay, my focus is being redirected in all sorts of different places. I need to chill. Right? We need to chill. Blue, 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 blue. Blue, 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 blue. Okay. In the last chapter, we discussed reciprocal space and explained how the energy dispersion of phonons and electrons is plotted within the Brillouin zone. We understand how electrons and phonons are similar to each other due to the wave-like nature of both. However, much of the same physics occurs when a crystal scatters waves that impinge upon it externally. Indeed, exposing a solid to a wave in order to probe its properties is an extremely useful thing to do. The most commonly used probe is X-rays. Another common, more modern probe is neutrons. It can hardly be overstated how important this type of experiment is to science. Why are X-rays used to probe crystals? See, you gotta get ChatGPT to role play. You gotta be like, listen, okay, you gotta be a fucking genius right now. Because their wavelength is on the same order of magnitude as the distances between the planes. Oh, okay, that's all you had to say. I'm so tired. I'm actually so awake right now, guys. I'm wide awake. Yeah, I was in the dark. Been searching for so long, but yeah, it's too late. Ba-da-ba-da-ba-da-ba-ba. Wouldn't dive in, wouldn't bow down, gravity hurts. Would I have a better time streaming on Twitch? Should I just stream on Twitch right now? Should I stream on Twitch right now? Like real quick? Like just stream on Twitch? Should I try that once? I might try doing that once. Today, right now. Should I try streaming on Twitch right now? Oh, should I? Let's try it, I guess. Like, let's just try it. I do want to multi-stream though on YouTube and Twitch. That would be the best case scenario. Or maybe stream on Kick. Should I become a Kick streamer? I don't know, dude. I feel like Twitch is just, honestly, like YouTube discoverability used to be the bomb, but I feel like now Twitch's discoverability is just better because less people are on Twitch now. That's just my feeling. Should I stream on, should I try? Let me see. Stream. I can try. I can try. I can try. I can try. Should I just do that right now? Should I just stream on Twitch? Let's try it, guys. No, not yet. Let's not try it today. Let's try it for next stream. Just because if anything goes wrong there, it's going to cause me a whole time to like be distracted and like try to get it solved and shit. And I don't want to deal with that right now. Okay. Wavelength matching. Yep. Penetrative ability. They can penetrate deep. Minimal damage. Okay. This is actually a really good short summation of everything that this chapter is going to be talking about, just leaving out like the math and physics of it. Okay. The general setup that we will examine is shown in figure 14.1. Yes. So I read through some of this previously, but yeah. So if we think of the incoming wave as being a particle, then we should think of the sample as being some potential VR that the particle experiences as it goes through the sample. According to Fermi's golden rule, the transition rate, blah, per unit time for the particle scattering from K to K prime is given by, so the transition rate is 2 pi over h bar. This matrix element, the amplitude squared of it, and this matrix element is written in this form, where you have the potential, you have the complex conjugate of k equals E divided by, oh, it's just a normalization. Okay, that's just a normalization factor. You have 1 over L cubed. Derivative of this. Yes. Makes sense. My S's today are sounding weirder than usual. Sometimes I don't know, it's like the tip of my tongue is just kind of weird. I need a sharper tick. I don't know. I need a speech therapist, man. Get rid of this slight lisp that I have, but ugh. Yes, I have to double grip the bottle right now because I can't grab it with this thing in my way. Okay. The matrix element is nothing more than the Fourier transform of the potential. We don't really need to fucking focus on that. However, if the sample is periodic, the matrix element is 0. If the sample is periodic, the matrix element is 0 unless k minus k prime is a reciprocal lattice vector. To see this is true, what? Okay, let's just read this. Periodic potential in a crystalline solid, atoms are arranged in a periodic lattice, and so the potential V of R that a particle experiences is also periodic. Mathematically, this periodicity can be described as this. The Fourier transform of a periodic function can be decomposed into sum over discrete points in a reciprocal space, which correspond to the reciprocal lattice vectors G. The presence of the delta function in the expression for the transition rate indicates conservation of energy. When you integrate the product of that and that over all space, you're essentially integrating complex. Yes. This integral is non-zero only when the exponential is constant, or equivalently, when k minus k prime is a reciprocal lattice vector, because only then does it describe a stationary wave over the whole crystal due to the periodicity of the crystal lattice. Otherwise, the complex exponential oscillates rapidly as r varies over the crystal, and the integral averages to 0 due to destructive interference. Okay, I guess. So this is known as the Lau equation. This condition is precisely the statement of the conservation of crystal momentum. Note also that when the waves leave the crystal, they should have k equals k prime. I'm like not in a state to absorb any of this right now. I'm like a particle. Yeah, we got a lot. Holy shit. Okay, I'm actually really tired. I should at least just get through 14.1. I'm just not focused. Why am I not focused? Pause that. Maybe we don't need music. Maybe we don't even need the headphones on. Maybe I'm turning a new leaf. Maybe I should have the music off for you guys, but not for me. Seems fine. Okay. Okay. So let us write the positions r equals r plus x, where r is a lattice vector position and x is a position within the unit cell. So this is now equal to this, a summation of r of the integral over the unit cell of dx e to the negative I k prime minus k dot x plus r v x plus r. Now, since the potential is assumed periodic, we have v x plus r equals v of x. So this can now be rewritten as r. Okay, so you take this, you multiply it in, so you get two of these, right? So you get that over r, and you have to integrate as well. Wait, why are you able to pull that out? Are you able to pull this out because it's like, why are you able to? Because it depends on r, and I guess now you're integrating over x. Because you're changing r equals r plus x. So dx. Yeah, I guess, because now dr is going to be equal to the derivative of a constant, where r is a lattice vector position, so it's a constant, and then x is some random position, so you take the derivative of that. So then dr becomes dx. So now you're integrating over dx, so anything with r dependence you can pull out because it's a constant. And then anything with x dependence you keep in there. And since it's assumed periodic, then you can write v x plus r equals v of x. Okay, so now your matrix element is now that. So the first term in brackets must vanish unless k prime minus k is a reciprocal lattice vector. This is so cute. He's barking along with Yesterday by Paul McCartney. And then one of the comments is Paul McBarkney. Which is so cute. I know, okay. I know exactly what you're thinking.
Is the answer when it comes down to performance versus strength.
Давай. Красивый мальчик. Держи. Какие красивые ноги. Молодец.
Welcome to episode 2 of Free Gal Diaries, where I
10 things in my apartment that I love.
welcome to day 1 of
I'm in the Philippines and I'm looking at a traditional Manila house, a mixture between Spanish stone houses and traditional tropical Asian architecture. Wonderful lessons about tropical architecture and ventilation. So many lessons. Favorite thing about architecture in the Philippines is the quality of the light. Very dark interiors, dark timbers, which is great when it's really hot outside. Huge openings for ventilation. And then you got these wonderful screens that you can come and slide and choose how you want it to be. These screens are made out of oysters shells, which is a local product. Not only does it diffuse the light, but also great thermal properties to stop the heat coming in. Further to that, you have traditional louvers. Again, you can close it off from the street but still have great flow of air and ventilation. Let's
Hey everyone.
UC Berkeley decisions are out. Today we'll be asking Berkeley students why they chose to come to UC Berkeley. No, why did you decide to commit to UC Berkeley?
UC Berkeley was my sister's dream school, and she paid for my application to come here. And just seeing how much she believed in me to come to a school like UC Berkeley, I was like, you know what? That motivated me to be like, okay, let me look into the school.
The campus a while ago, and it's super pretty, and I love the bay, surrounding area.
Who the fuck says the campus is pretty, dude?
Why should students come to UC Berkeley? Okay.
Wanted to get as far away from Kansas as possible, and also because my brother's here, so that's pretty cool.
A lot of factors. I'm from SoCal. I'm from Santana.
I don't know what it is. Okay, this is gonna get me canceled. I don't know what it is. Okay, but like when anybody else is saying like another, like, you know, like a place, but they're like speaking English. If they're saying like a foreign place, but they're speaking English, you know, any other person is gonna be like, oh, where are you from? And they're like, oh, you know, I'm from Beijing or something like that. You know, like, oh, I don't know, I'm from Jamaica, you know, something like that. But anywhere that's like Spanish speaking, it's always got to be like, oh, I'm from Venezuela, you know, like they gotta say it like exactly how it would be pronounced in Spanish, which I get, you know, like you shouldn't like bastardize it. You shouldn't be like, what's a good example? Like, oh, I don't know, I'm from, I don't know, Argentina. Like you shouldn't just bastardize it and like mess it up. But at the same time, you know, there's like when you're speaking it in English, you kind of like translate it to English, you know, you're like I like, you know how like in Japanese when people are like, if people had to say like, oh, like I am like I'm eating hot dogs or whatever. Let's just say they're saying I am a hot dog. Okay? And they'd be like, watashi wa, like if I was English, all right, and I was telling a Japanese person that like I am a hot dog, I'd be like, watashi wa hot dogu. I wouldn't be like, watashi wa hot dog. You know? No. Actually, you know what? I might have changed my mind. No, I changed my mind. Talking it out, I kind of changed my mind. You know what? Yeah, you can be like, oh, I'm from Venezuela. Oh, I'm from Mexico. I think that's okay. It's okay. It's fine to do that, I think. It's probably not necessary. Because I was just thinking, like, would I feel the same if, like, people were like, oh, I'm from Iran, instead of saying, oh, I'm from Iran? But no, you should say it Iran. I don't even know where the pronunciation Iran came from, though. That's just kind of like a dumb pronunciation, though. Because, like, we do say stuff that's, like, starts with an I, like E, in some cases. I'm sure there's one. I don't know why I put these on. Anyways, guys, I'm getting distracted, aren't I? Okay, this is that. Yes. I get it. So the first term in brackets must vanish. Only vanishes if, I think they meant to say that, only vanishes if k minus k prime or k prime minus k is a reciprocal lattice vector. Yeah, this is equal to G. Then I don't know. Hold on. They probably uploaded some. My GSI probably uploaded something related to this in the notes. Let's check it out. Check it out. Check it out. Who the fuck is messaging me? Okay. Brother, yeah, the mathematics is really hand wavy here. Cause this shit is fucking stupid. Oh, let's take out the Ashcroft and Mermin textbook actually. Boom, Ashcroft and Mermin. Holy guys, holy. I need to go to chapter 695. Right here. Since the lattice sides are displaced from one another by the Bravais lattice vectors are the condition that all scattered rays interfere constructively is that condition 6.5 holds simultaneously for all values of d that are Bravais lattice vectors. So r dot k minus k prime equals 2 pi m. This can be written in the equivalent form e to the I k prime minus k dot r equals 1. Comparing this with the definition of the reciprocal lattice. Okay, I guess I just need to look at the fucking reciprocal lattice. E to the I g dot r equals 1, where r are points of the reciprocal lattice. And then what is this? Where r is a point in the reciprocal lattice. Oh. Yeah, so for this to be, what, non-zero? For this to be non-zero, and this has to be G. I don't get why it has to be G to be non-zero. Mathematically, this integral is only non-zero when k minus k prime equals g. If k minus k prime does not equal a reciprocal lattice vector, the exponential inside the integral represents a wave that is not stationary with respect to the crystal lattice. And the integral will cover whole periods of this wave, leading to zero. Bro, can someone just fucking show me a picture? Someone show me a picture of what this means. Physically, the requirement that k minus k prime equals g represents a conservation of quasi-momentum in the crystal. The crystal can only absorb or provide momentum in quantized chunks corresponding to its reciprocal lattice vectors due to its periodic structure. When a particle... Oh my god, this fucking thing on my neck is... Oh, it's fucking annoying. When a particle scatters within a crystal, its momentum change must correspond to these quantized values. When a particle scatters within a crystal, its momentum change must correspond to these quantized values. Otherwise, the scattering process is not allowed by the symmetry and periodicity of the lattice. Hence, the matrix element is zero unless this condition is met. It's the probability of transition between those two states. Bro, who the fuck is messaging me, brother? No one was messaging me. I just heard a buzz for no reason, because I'm insane. Yes, guys, you heard it here first. I'm physically insane. Okay, this is the transition probability, which is right here, right? So we're saying the probability is this is transitioning, or the overlap. So the matrix element is just the overlap between this and this. So it's saying like how much of it is scattering. How much of the incident is becoming the scattered, aka how much is this incident scattering? And so we're saying this can only exist if k minus k prime, we take k minus k prime, and that equals g, which is a reciprocal lattice vector. Can we just watch a YouTube video on this? How good is this YouTube video gonna be?
Elastic scattering of X-rays, first from an electron and then from an atom with multiple electrons. This lecture we're going to look at the scattering from a periodically repeating set of atoms, that is from a crystal.
Gonna say I'm not hopeful.
You can find a lot of treatments of this material in the literature. They're scattering in all directions. But if this was the whole story, that the X-rays came in and the atoms radiated out X-rays of the same wavelength in all directions, that wouldn't be very useful. We could not figure out the structure of a crystal. We could not figure out the spacing or the geometry of atoms in a crystal from that kind of information. So there has to be something more to it. And that something more is the interference effects that arise because some X-rays are going to travel different distances than other X-rays. Remember in the last lecture, we said if we have one photon that might have this oscillating sinusoidal repeat in its electric field, and then we had this photon interact with another X-ray photon of the same wavelength, but phase shifted by some amount. And what we learned is that the constructive or destructive interference between the two photons would depend on the phase shift. So if the phase shift were 90 degrees, we would get a wave whose amplitude is actually going to have the same maximum and minimum of both of the photons that are interfering. If we had a wave that was shifted by 150 degrees, we see that the amplitude of the wave has now been diminished, so there's more destructive interference than constructive interference. And then over on the right, we see the extremes of a 180 degree, or pi, phase shift, which leads to completely destructive interference. The waves cancel each other out. Or a 360 phase shift, or that would be 2 pi in radians, that leads to fully constructive interference. So when we think about diffraction from crystals, what we're looking for are certain directions of the X-ray through the crystal that lead to this fully constructive interference. And in the other directions, we're going to see varying amounts of destructive interference. Now, if you just have two X-rays interacting and they're a little bit off, or even maybe a lot off, like these images on the left here, it doesn't totally cancel each other out. But now if you were to have 1,000 or 1,000,000 X-rays that were all interfering with one another, and they're all off just a little bit, you don't have to get very far out of the fully constructive condition until you get the X-rays almost completely canceling each other. So where we see diffraction peaks in a pattern is going to be angles where we can maintain this fully constructive interference between different X-rays that are being scattered by different atoms in the crystal. All right, let's go back to our line of atoms, our one-dimensional crystal. Let's have one X-ray come in. We'll call this wave A. It comes in at a certain angle. And then we have wave B that comes in parallel and in phase, but scattering off a different atom in our crystal. We need to define some geometric parameters here. We can say that the spacing between atoms in the crystal is A, right? And because it's a one-dimensional crystal, all of the atoms are going to be this distance apart. We can say that the angle that the incoming X-ray beam makes with this row of scatterers is theta 1. And then the angle that the scattered beam makes with the row of scatterers is theta 2. And theta 1 and theta 2 are not necessarily equal. So what is going to be the interference effects, or the phase shift, if you will, between these two waves? Well, we can do a little trigonometry here. Let's define a right triangle here. And the significance of this dashed line is that the waves are in phase coming in. Okay, so their peaks are lined up, and they've traveled exactly the same distance until they get to this dashed line. But once they reach this dashed line, wave A is scattered elastically by this atom. Okay, so now it's on a different path. And the distance that's marked here with the red line, that's going to be the extra distance that wave B travels before it is scattered. On the scattering side, we can draw another line that is perpendicular to the waves, and this is another right triangle here. Wave A is going to travel an extra distance from 1 to 4 before they're back lined up with one another. So the difference in path length between wave B and wave A is the distance from 3 to 2, that's the extra distance that wave B travels, minus the distance from 1 to 4, which is the extra distance that wave A travels. Now, trigonometric relationships tell us that this red line here, right, this is a right triangle, and the hypotenuse of that triangle is A, the spacing between the atoms. So the length of this leg of the triangle is going to be the hypotenuse A times the cosine of theta 1. By the same token, if we look at the right triangle formed from 1, 2, and 4, we see that this blue line is going to be the hypotenuse A times the cosine of theta 2. So the path length difference is given here, A cosine theta 1 minus A cosine theta 2. And for constructive interference to occur, fully constructive interference, we want that path length difference to be a multiple of the wavelength. Of course, when theta 1 and theta 2 are equal, the path length difference goes to 0. And so in that case, we maintain full constructive interference. And that case would be something like this plane of atoms acting as a mirror. The scattering angle in and the scattering angle out, theta 1 and theta 2, are equal to one another. Now you might ask the question, well, could there be some other angles where we might get constructive interference because the path length difference could be one wavelength or two wavelengths? The answer is that can happen, provided that the wavelength is shorter than the spacing between the atoms. We'll come back to that later. But for now, the key point to think about is that when the angle in and the angle out are the same, we don't introduce a path length difference, and so we get constructive interference. Okay, now let's add a second plane of atoms, which is offset by this distance d. Now let's look at how these two rows of atoms will scatter X-rays. So let's have wave 1 come in at some angle theta and be scattered off an atom in the first plane. The angle that the incoming X-ray, which is represented by the unit vector S naught, that's its direction. The angle it makes with the plane of atoms is theta.
Let me try to recap this. So we have some wave A that's coming in, some wave B that's coming in, and we're saying up until this point right here, they've pretty much traveled the exact same distance. So we're saying that this extra distance, so these distances,
angle that the scattered
so what are we saying?
Makes with the row scatterers is theta 2. And theta 1 and theta 2 are not necessarily equal. So what is going to be the interference effects, or the phase shift, if you will, between these two waves? Well, we can do a little trigonometry here. Let's define a right triangle here. And the significance of this dashed line is that the waves are in phase coming in. Okay, so their peaks are lined up, and they've traveled exactly the same distance until they get to this dashed line. But once they reach this dashed line, wave A is scattered elastically by this atom. Okay, so now it's on a different path. And the distance that's marked here with the red line, that's going to be the extra distance that wave B travels before it is scattered. On the scattering side, we can draw another line that is perpendicular to the waves. And this is another right triangle here. Wave A is going to travel an extra distance from 1 to 4 before they're back lined up with one another.
Oh, so this is when their phases are back in line, basically, is at this point.
The difference in path length between wave B and wave A is the distance from 3 to 2.
Because at this point, they're in sync, and then after this is bouncing and it's out of sync this way. They're out of sync, but then when they reach this point, it's going to bounce. This one's going to keep going, and then they're going to be in sync again.
That wave B travels, minus the distance from 1 to 4, which is the extra distance that wave A travels. Now, trigonometric relationships tell us that this red line here, right, this is a right triangle, and the hypotenuse of that triangle is A, the spacing between the atoms. So the length of this leg of the triangle is going to be the hypotenuse A times the cosine of theta 1. By the same token, if we look at the right triangle formed from 1, 2, and 4, we see that this blue line is going to be the hypotenuse A times the cosine of theta 2. So the path length difference is given here, A cosine theta 1 minus A cosine theta 2. And for constructive interference to occur, fully constructive interference, we want that path length difference to be a multiple of the wavelength. Of course, when theta 1 and theta 2 are equal, the path length difference goes to 0. And so in that case, we maintain full constructive interference. And that case would be something like this plane of atoms acting as a mirror. The scattering angle in and the scattering angle out, theta 1 and theta 2, are equal to one another. Now you might ask the question, well, could there be some other angles where we might get constructive interference because the path length difference could be one wavelength or two wavelengths? The answer is that can happen, provided that the wavelength is shorter than the spacing between the atoms. We'll come back to that later. But for now, the key point to think about is that when the angle in and the angle out are the same, we don't introduce a path length difference, and so we get constructive interference. Okay, now let's add a second plane of atoms, which is offset by this distance d. Now let's look at how these two rows of atoms will scatter X-rays. So let's have wave 1 come in at some angle theta and be scattered off an atom in the first plane. The angle that the incoming X-ray, which is represented by the unit vector S naught, that's its direction. The angle it makes with the plane of atoms is theta. And then the scattered or diffracted X-ray, which follows this direction S, its angle is also theta. And we saw on the last slide that we're still going to have constructive interference when these two angles theta are the same. Now, if we had another X-ray that would not scattered by the first row of atoms, but is scattered by an atom in the second row, or the second plane of atoms, its path would look like this. So the question becomes, what is the path length difference between these two X-rays? We're going to draw some right triangles here, right? So these dashed lines are perpendicular to first the vectors S naught, and here the vector S. And the path length difference, if it's equal to an integer number of wavelengths, is going to lead to constructive interference. So n here is just an integer, and lambda is the wavelength of the X-ray radiation. That path length difference on our diagram is the distance from 1 to 2 and 2 to 3. Now, a little trigonometry, though, tells us that if the hypotenuse of our triangle is d, the spacing between planes, if this angle is theta, then it means that this angle also must be theta. And the length of this leg of the triangle then is going to be d times sine theta, right? Sine is the opposite over the hypotenuse if we have a right triangle. And so the total path length difference is going to be 2d sine theta. And if that equals an integer number of wavelengths, then we're going to get constructive interference. And this relationship, n lambda equals 2d sine theta, probably one of the more famous equations in science. This is called Bragg's law, named after the father and son team, the Braggs, who discovered this relationship in the early 20th century, and then used it to determine the structures of several simple crystals. We might also rearrange this if we were so inclined to say that the angle theta that satisfies this condition is the arc sine of n lambda divided by 2d. Let's go back to our one-dimensional crystal, this row of atoms that can scatter X-rays. And let's ask the question, if we're so inclined to say that the angle theta that satisfies this condition is the arc sine of n lambda divided by 2d. Let's go back to our one-dimensional crystal, this row of atoms that can scatter X-rays. And let's ask the question, are there any angles other than being reflected at the same angle that the beam comes in at that would lead to constructive interference? So for this derivation, we're going to allow the X-rays to be scattered not only in the backward reflection direction, but also in the forward transmission direction. And we've got some relationships here. So our incoming X-rays are coming at this angle with respect to our crystal. Right? Our crystal is vertical here. And the direction of the incoming X-rays is represented by the vector S naught. The angle which S naught is making to our crystal is we're going to call alpha naught. And then we're going to say that the scattered radiation is described by the unit vector S, and it makes an angle alpha with the crystal. And alpha naught and alpha are not necessarily equal. So under what conditions might we get constructive interference? Well, let's go back to this drawing of right triangles and use some trigonometry to figure out the path length difference. So the upper wave here, it travels an extra distance of 4 to 2 than the lower wave before it's scattered. And then after scattering, the lower wave travels this extra distance of 1 to 3. So the path length difference is simply the distance from 1 to 3 minus the distance from 4 to 2. Now, for constructive interference to occur, we need this path length difference to be an integer multiple of the wavelength. So we can write down an expression. H is just an integer times the wavelength. That's going to be equal to, this vector 1, 3 is just a, the distance between scatterers, which is the hypotenuse of this right triangle, times the cosine of the angle alpha. That's the scattering angle. The red vector is going to be, once again, a, still the hypotenuse of this triangle, times the cosine of alpha naught. If we know alpha naught, that is, we can control the angle that the incoming X-rays make with our crystal, and we could solve then for what is the angle alpha that would lead to constructive interference. First, we isolate the cosine alpha term on one side of the equation, and then if we take the arc cosine of this argument here, cosine of alpha naught plus h lambda over a. That is known as the Laue equation, and we can use this equation to see the angles at which constructive interference might occur when the X-rays pass through and are scattered by the atoms in our crystal. Let's look at the case where the incoming radiation is perpendicular to our crystal. So we can think of our crystal as being vertical, and the incoming radiation is traveling horizontally. In that case, the angle between the two, alpha naught, is equal to 90 degrees. So here's our Laue equation, and we can plug in 90 degrees for alpha naught, and then we can also specify the distance between the atoms, and this distance is going to be 2 times the wavelength of the radiation, 2 lambda. We're going to put those values in for alpha naught and a into our equation. Now the cosine of 90 is 0, and the lambdas cancel, so we're left with the angle or angles at which constructive interference occurs will be those that are given by the arc cosine of h over 2, where h is an integer. Well, what are the solutions to this equation? Are there an infinite number? Are there a finite number? Well, if h equals 0, then the angle would be 90 degrees. And that's, in a way, just a trivial result. That is, diffracted radiation is continuing on exactly the same path as the incoming radiation. Right? That makes a 90-degree angle with our crystal. What about if h equals 1? Well, in that case, we have the arc cosine of a half, and that's 60 degrees. So in that case, we can see that when the scattered radiation makes an angle of 30 degrees with the path that was coming in, we're going to get constructive interference. And if h equals minus 1, then we get an angle of 120. So we can see that these two beams, which are deflected either 30 degrees on either side of the direct beam, are going to give us constructive interference. Well, what about larger values of h? Well, if h is equal to 2, then we have the arc cosine of 1, and that's going to be 0 degrees. And if h equals minus 2, we would get 180 degrees. So that's the vertical direction up and the vertical direction down in this diagram. They would be scattered along the row of atoms. Now, larger values of h are actually not going to give us any scattering, because if h were any larger, let's say like 3, then our solution would be arc cosine of 3 halves. Well, the cosine function only goes up to 1, and so the arc cosine of anything bigger than 1 is not defined. And so what we see is we are only going to see diffraction effects if the spacing between the atoms here, between our scatterers, is larger than the wavelength of the radiation. So then you start to see why you need to use X-rays. You need to use some kind of electromagnetic radiation whose wavelength is comparable to, and ideally a little bit shorter than, the spacing between atoms in a crystal. And that's why we have to use X-rays. Now we could also look at this in another way. Let's say this incoming beam comes in, it's deflected at an angle of 30 degrees with respect to its original direction. That would be constructive interference. But there's not just one vector that makes an angle of 30 degrees with this initial vector. It can actually be scattered in all of the vectors that are pointing along this cone. Right? So we get a diffraction cone, all of which have h equal to 1 in that equation. We have another diffraction cone for h equals minus 1. And the scattering for h equals 0 could be anywhere in the plane that contains the incoming vector. So we get cones of diffraction, along which we see constructive interference, and those cones radiate around the axis of our one-dimensional crystal. If we were to wrap a cylindrical detector around our crystal, we would see something like this. We would see dark lines. Let's say it was a photographic film, and we got a dark line anywhere that the X-ray radiation hit the film. Well, we would see a dark line at this point, and then we would see one up here. And if our detector were perfectly cylindrically curved, these would be straight lines. From our vertical crystal, we're going to get horizontal lines at which we're going to get constructive interference, and these are called the diffraction lines. Let's increase the spacing of the atoms in our crystal. Remember in the last example that they were 2 lambda apart from one another. Difference is here, third, and so we get an angle of either about 7. To put it is we could say that. So we can kind of summarize what we've learned about scattering from a one-dimensional crystal. First of all, we learned that construct and S naught is a unit vector which describes the direction of the incoming radiation. Using the properties of vectors, we can rewrite this as A times the dot product of S minus S naught. This is the form of Lowey's equation that we will typically use. We could just kind of think about it for a minute here. S minus S naught is going to be a vector that's going to be in the vertical direction. And as that vector gets larger, then the dot product of it with A is going to get larger. And so there's only going to be certain times when that dot product is an integer multiple.
Okay, this video is useful for the trigonometric or geometric kind of approach, but not for this kind of approach.
In this video, in order for those if to the defining equation coming wave vector k, we can measure. In this video, we will explain the Laue condition, which is a general form of the Bragg condition and describes how waves can scatter at a lattice. Both the incoming and the outgoing X-ray waves can be written in terms of cosine functions, where we assume monochromatic light for simplicity. The incoming wave has a wave vector k, and the outgoing wave has the wave vector k prime. For now, those two mathematical expressions don't have anything to do with each other. So let's think about what physics they represent. In order for those two cosines to represent scattered X-rays, they have to meet at some point in the crystal lattice. And, what's more, they have to be in sync, which means their phase should be the same. And this should be true for any point x in the lattice. If we rearrange this equation a bit, we get the result that k prime minus k times x has to be equal to 2 pi times some integer n. Again, x represents any lattice point, so we can write it in terms of lattice vectors A. Compare this to the defining equation of the reciprocal lattice vectors. We see that if k prime minus k is equal to a reciprocal lattice vector, the equation is automatically fulfilled, and we get constructive interference. This is the Laue condition. By doing an experiment, we know the incoming wave vector k, we can measure the outgoing wave vector k prime whenever the lattice. If we rearrange this equation a bit, we get the result that k prime minus k times x has to be equal to 2 pi times some integer n.
Okay.
Again, x represents any lattice point, so we can write it in terms of lattice vectors A. Compare this to the defining equation of the reciprocal lattice vectors. We see that if k prime minus k is equal to a reciprocal lattice vector, the equation is automatically fulfilled, and we get constructive interference. This is the Laue condition. By doing an experiment, we know the incoming wave vector k.
So this is just making the argument that for an incoming and outgoing thing to be the same phase, then that means that it would have to satisfy this. And it can only satisfy this if this is actually the reciprocal lattice vector. Is that what the fucking thing is saying too? This sentence is like... Let me not get mad. The first term in brackets must vanish. Unless this must happen, unless, so this vanishes unless, so this stays. So if this must vanish unless this, so this must happen if this is not, like, what the fuck? You can just reword this. The first term in brackets must vanish, so it must do a negating thing if this thing is negated, like the fucking way this is phrased, man. The first term in brackets must vanish unless k prime minus k is a reciprocal lattice vector. I think this video does a decent job at just laying it out, I guess.
We get. In the case of Bragg scattering, the wave vector only changes direction, not magnitude. Therefore, k squared is the same as k prime squared. If we write the lower condition as k being equal to k prime minus g, we can square this equation and subtract k squared from both sides, since it's equal to k prime squared. Next, we simplify the inner product by using the cosine of the angle between k prime and g. A quick look at the drawing of Bragg scattering reveals that this angle is equal to pi over 2 minus the incident angle, which is usually called theta. And the cosine of this is equal to the sine of theta. Next, the wave vector is given by 2 pi over lambda, and g is given by n times 2 pi over the lattice distance d. And really, rearranging this equation yields the usual Bragg condition for constructive interference in X-ray scattering. In other words, the lower condition can be seen as a more general case of the Bragg condition. And that's pretty much it for this video. Thanks for watching.
Okay. Sure. I feel like everything's lying to me. I feel like ChatGPT is just getting worse as well, dude. It's just fucking getting worse. Okay. Like, why not say that this needs to be enforced because we're just assuming that when a wave comes in, it elastically collides with the atom, perfectly reflecting it off. And so if it's perfectly elastic, then that means that their phases, like, they have to be in phase. The frequency coming in has to be the same as the frequency coming out. So you need these wave vectors to be the same. And by the way, this is also just another way to describe conservation of energy. Not just being like, oh, this has to equal that because conservation of energy. Like, what? That's like saying, hey, why is it that when I play pool, when I play billiards, when I hit a ball, one stops and then one keeps going, and then I'm like, oh, conservation of energy. Like, what the fuck? That's like me asking, hey, like, blah, 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 like, how do I fix this phone? And they're like, oh, principle 2.3. Why not just say what it is? Oh, the billiard ball stops because when this is going, all of its energy, all of its kinetic energy is transferred onto this ball perfectly because their collisions, we're going to assume that these collisions are elastic, perfectly elastic, which means that no energy is dissipated through friction or anything else. So once this collides with that, it transfers all of its energy over. This is what we call conservation of energy. Like, I don't know. No, you know what? No, we should write every single fucking textbook using just, using the shortest words that we can use so we don't have to describe anything. That's correct. I'm getting really frustrated. I need to stop. Need to breathe a little bit. Okay. Diffraction approach. It turns out that this Laue condition is nothing more than the scattering condition associated with a diffraction grating. this description, I'm glad. I'm being negative again. I'm glad that you went with the formulation of like using fucking quantum mechanics, like expectation shit, you know, probabilities of transmission, rather than just going with a simple geometric argument first. But that's cool. Even fucking Ashcroft and Merman. I don't think they mention anything that has to do with like quantum mechanics, right? Until later, maybe? No, they don't. They just use a whole bunch of geometry. Maybe this? No, it's still just mainly geometry, right? Yeah, they don't use Fermi's golden rule. Okay, we saw videos going through this. This is such a bad fucking... Like, I don't know. Yeah, it's going to be 2d sine theta, because you take into account both of these for their path to be the same. Yeah, and it has to be, yeah, to be constructive, it has to be an integer number of wavelengths. So it's equivalent to say that the interference is constructive or to say that the crystal momentum is conserved. Okay. This is a long chapter, dude. Maybe I should maybe I should have just did math. I'm tired. I think it's too late in the day to like take a nap. Do I just go to sleep, I guess? Okay, I'm gonna vent a little bit. Like, studying is just so much... Like, it's just so much harder than, like, just doing something that's tangible. Like, oh, go do this, or go, go do this. Like, go study that, like, takes so much different fucking components, especially when your fucking textbook is not straightforward, or I guess the material is just not straightforward. I mean, like, look at this shit. Look at all of this, man. I do need to understand scattering amplitudes, though. Bruh. I need to understand it, but I'm not in a state right now to, like, really understand it. You know what I mean? I don't even think we need to read 14.3 and 14.4, honestly. I think it's just 14.2. Okay, if anything, I'm gonna fucking take a nap. If that nap turns into a sleep time, then it's sleep time, I guess. What are you gonna do? Alright, that's it for now. My brain is exhausted. Maybe I just need to take a break, because I had a long day. Yeah, okay. Peace.